At the center of lesson 10 is the fundamental theorem of calculus. In a way, you can think of it as the crowning achievement of our course, because it incorporates all the concepts, the central concepts that we have learned about, namely differentiation and integration, continuity, and so on. So what I want to do in this lecture is go over several problems that use or deal with the fundamental theorem of calculus in various ways, and that are, again, very similar to problems on the quiz, and that way hopefully give you a better understanding what the fundamental theorem is and how to use it. So here's the statement of the fundamental theorem of calculus as a formula. So suppose we have a function f whose derivative exists, f prime, and we also need to assume that this is f prime is continuous, which is mostly the case in our application, so we don't have to worry too much about it, but it needs to be said. So if f prime is continuous, then the definite integral from a to b of f prime is the total change of the function between a and b. Right? So f of b minus f of a. So in one sense, this theorem tells us that integration is indeed the inverse operation to differentiation, because what it says, if I start out with the function f, take the first derivative, right, and then integrate, I get not quite the original function back, but something that is very closely related to the original function, right? Because it's the total change of the original function over the interval over which you integrate. So the way it's written here, it emphasizes that if I start out with the original function, take the derivative, integrate, I get the total change of the original function back. There is a version of the fundamental theorem of calculus, it's often called the second fundamental theorem of calculus, that makes this connection between derivative and integration as inverse operations even clearer. So you'll find that if you're interested, you'll find that in the section Focus on Theory. It's quite interesting, so give it a look. Let's write the fundamental theorem in a little bit a different way. So for that we need the notion of an antiderivative. So as you can probably imagine from the choice of words here, an antiderivative is pretty much what you would do if you go in the opposite direction. Instead of taking derivatives, you get you go up, you look for antiderivatives. In other words, capital F as a function is an antiderivative of a function little f if capital F prime, so the derivative of capital F, is little f. So, and now we can write the fundamental theorem of calculus as follows. So suppose f is an antiderivative of little f, and again suppose that f is continuous. Again, I'm just writing this because it needs to be, this assumption needs to be made. Then we can get the definite integral of little f from a to b as simply the difference of capital F of b minus capital F of a. So here, this version emphasizes really that the fundamental theorem of calculus gives us a great way to compute definite integrals, right? Because all we need to do to compute this integral is to find an antiderivative of the original function and then just subtract the two values of the antiderivative at the boundaries of the integration interval. So So that's very nice. So as you can hopefully see now from these first few slides, is that the antiderivative plays a central role here. And what I want to do now is to go over several problems and facts that are important to know about antiderivatives. That means, for instance, how to find them and how to use them in these various settings. So the first important thing to realize about antiderivative is that the antiderivative of a function is not unique. So remember when we did derivatives, if I take the derivative of a function, there is exactly one function that is the derivative of that function. Okay, that's not so the case anymore for antiderivatives. So take, for example, the function f of x equals 2x. Right? If we're looking for antiderivatives, we could take the function capital F of x equals x squared, right? Because clearly the derivative of this function here is 2x. But as you easily see that, for instance, f tilde of x, x squared plus 5, is also an antiderivative, because if I take the derivative of this function, we get 2x, and 5 just vanishes by taking derivatives, right? So here we have two different antiderivatives that are different functions, but they give the same little f, they have the same derivative, right? In general, of course, as you will see, any function of the form x squared plus c, where c is a constant, right? 5, or here it would be 0, or it could be 1, could be 153, right? Or minus, right? So minus 15. Any function of this form is an antiderivative, right? And so that makes the business a little bit more complicated, but not by much. The important thing is to remember that it's not a unique, and it's only determined up to this constant here. Right? So if you have an antiderivative, adding a positive or a negative constant c to it, then it still stays an antiderivative. And that's why this notation of the indefinite, or notion of the indefinite integral, is introduced to capture this family of antiderivatives in one expression, right? So when you read about the indefinite integral, for instance here 2x dx, right, would be x squared plus c. That just says this here, right, is, if it doesn't have bounds, it's an indefinite integral. And it means it's not a number, but just a family of functions, namely the family of all antiderivatives of the original function. Right. So this is the notational concept of an indefinite integral. It is just meant to collect all these different antiderivatives in a single expression. But do not forget, when you do indefinite integrals, there always is like this plus c, right? Because it's really necessary, because the antiderivative is not unique. So while we cannot speak of the antiderivative, but only of an antiderivative of a function, right? For the fundamental theorem of calculus, it does not really matter, right? Because if you write ab little f of x dx as f of b minus f of a, right? And now let's say we replace f by another antiderivative, right? So let's stay with our example, ab 2x dx, and let's first, so that would be b squared minus a squared, right? Because the antiderivative of 2x is x squared. But we've also seen that it's that x squared plus 5 is also an antiderivative. So if I use this, right, for here our f x squared plus 5, I plugged in b and a, right, I would get b squared plus 5 minus a squared plus 5. And now you see what is happening, right? Because here we have plus 5, here we have minus 5. So these 5's cancel out by taking this difference, right? And we were left with b squared minus a squared, which is the same as using the antiderivative x squared, right? So there you see for this application here, it does not matter which antiderivative you use. It's just any antiderivative is fine. So while the antiderivative is only determined up to an additive constant, if I give you some additional information about the antiderivative that I'm looking for, so usually that's in form, and that's how it's done in the problems, it's in form of a single value of the function, and usually at 0. So if I say give you the value f of 0, so let's say in our example f of 0 is 3. So as soon as I give you a single value of the specific antiderivative I have in mind, so let's say f of 0 is equal to 3, then in our example here, as it does in general, if, for instance, here we have in our example f of x is 2x, the antiderivative, all antiderivatives are of the form x squared plus c. If I have this additional information, I can actually now use this additional information to determine the value of c. So in our case here in this example, we would have 3 equals f of 0, but f of 0 is also 0 squared plus c, right? Because that's the form that the antiderivative has to take. And now I see from this that c must be equal to 3. Right? So if I give you this additional information, the antiderivative is actually fixed. In our example, it would be x squared plus 3. So it's not always the case, though, so be warned, that it's if I give you f of 0 equals 3, then c is automatically the value of f at 0. So look, for instance, at this example, f of x is 2 e to the x. The indefinite integral, so the antiderivatives of this function are easy to determine because of the nice behavior of e to the x with respect to differentiation. We'll talk more about this later. Is 2e to the x plus c, right? So now suppose I give you the extra information that I'm looking for the antiderivative whose value at 0 is, let's say, 1. Right? Then I would know that 2e to the x plus c, right, or e to the 0, sorry, plus c is equal to f of 0 is equal to 1. So I would get, well, e to the 0 is 1, so I would get 2 plus c. 2 plus c is equal to 1. In other words, I would have c is equal to 1 minus 2, so it's minus 1. So here you see, it's not automatically that the value of c, right, is equal to the value that the function takes at 0. Right? So you really have to, if you want to determine the value of c, right, you have to set up this equation and then solve it for c. So let's go over a number of exercises that helps us familiarize ourselves with the notion of an antiderivative. So the first thing, and it's a really good exercise, but also not easy, that I want to do is to go over finding the graph of an antiderivative from the original function little g here, right? So you see here, we are given this extra information, right, of what the function value of g as at e0 is. So that means the antiderivative actually becomes fixed through this. So let's read the assignment first. So using this figure below here, sketch a graph of an antiderivative capital G of little g satisfying this. So again, this just has the effect that it actually fixes the antiderivative as we've seen before. Then label each critical point of g of t with its coordinates. I forgot to mention for your reference, this is 6.1 number 21. So from the book. So I've copied just the graph over to the next slide. And this additional information, capital G of 0 is equal to 5. So that we can start now to start drawing the graph. So let's start. So the first thing we observe is, well, here we have the function is positive and has total area 16 between 0 and 2. So we've already seen in the last session, the lecture, that the definitive integral is the same as the area under the curve if the function is positive, right? So we would have here that the integral from 0 to 2 of g is equal to 16, right? But we also know now from the fundamental theorem of calculus that this is the same as g of capital G of 2 minus capital G of 0, right? But we know capital G of 0 is 5. So we know that this area here, this area of 16, right? 16 is equal to G of 2 minus 5, which means that G of 2 is equal to 21. So that's one point we can enter here on our graph. I've started the graph already because we know that at 0 our function capital G has value 5. Now it goes up, right, to point, so we have 1 and 2, and it goes up to value 21 up here, okay? And now we can do the same thing as we did for capital G of 2 with the other areas that are given to us, right? So here we have a negative function value. That means that the definite integral from 2 to 4 is the negative value of this area. So the definite integral from 2 to 4 of g is minus 8, right? Because it's the negative value of this area. But we also know from the fundamental theorem of calculus again that this is the same as g of 4 minus g of 2. Okay. Right. Again, we can now combine this as we did here into one equation. So that would be, right, minus 8 is equal to g of 4 minus g of 2, but we've computed g of 2, namely it's 21, so minus 21. And now we can solve this for g of 4, and we get our value for g of 4, namely g of 4 is 21 minus 8, which would be 13. So in our graph here, it would be 3 and then 4 over here, and we would have a value of 13, so about here. Finally, we have a positive area again, right? Between 4 and 5, area is 2, right? We know that g of 4 is 13. Total area here between 4 and 5 is 2. That, by the fundamental theorem of calculus, is equal to the total change of the function from 4 to 5. The function starts out with 13 at 4, so at 5, since it's the total change, it must be 15. So same idea, so you can, if you feel more comfortable, just write down these equations again, right? So we have at 5 now value 15. Okay. So our function now will look something like this. Go up, have a local maximum at 2, go down, have a local minimum at 4, and go up to go over to 5. And so the problem also asked us to write in the coordinates for the critical values and the critical points. So that would be 0, 5, 2, 21, 4, 13, and 5, 15. I should have drawn this a little bit better here, so that you actually see that here we indeed have critical values. Right? We have horizontal tangents. So because you see what's happening here, now little g is our derivative, right, of this function. Whenever the derivative has zeros, we must have horizontal tangents or critical values in the original function, our capital G that we're looking for. Right? And we see we have zeros here, we have a 0 here, 0 here, 0 here. So all these are critical points. Okay. We could even infer a little bit more already about the function. I probably didn't draw this quite correctly now, but look, for instance, here. We know here our derivative, g, little g, right, of our big G function would have a horizontal tangent. That would mean at this point the derivative of little g would be 0, which in turn means that the second derivative of capital G, right, would have the second derivative would be 0. That means there would be an inflection point here. So somewhere just before 1, there would be an inflection point, right? And same thing here, just at about 3, there would be an inflection point in capital G. But this is not really asked here. It's just to give an idea of the graph. And I hope this technique, right, so you translate area, you write down the area as a definite integral, and you have to pay attention to whether it's positive or negative area, right? And then you use the fundamental theorem of calculus to equate these to a total change of the function that you're using, that you're looking for, namely the antiderivative, right? And this gives you an equation that you then can solve for the function value, and it gives you the function value. And so this gives you kind of the anchor points for the graph that you're asked to draw. There's a problem of this on the quiz of a very similar kind. And I hope now you feel confident to solve this kind of problem. So it's not easy, but do it step by step as we did here. So the next problem is also from the book. So this is from section 5.5. And instead of doing this graphically now, we see one of the interpretations of the fundamental theorem of calculus now with respect to cost functions. So far, we always had like the cost function given, right? And we wanted to know the marginal cost function. And we knew that this can be done using the derivative. Now we are given the marginal cost function, right, for a company is given by C prime, so marginal cost of quantity Q is Q squared minus 16Q plus $70 per unit. Right. We are also given the fixed total cost, right? The fixed cost of starting production. So that's cost at 0 units is 500. So that's what I always have to pay or take into account no matter how much I produce. Fixed costs are 500, right? C of 0. And we are asked to find the total cost of producing 20 units. So if we simply write this now, write up our fundamental theorem of calculus using these functions. So we would write 0 to 20 C prime of Q dQ, right? By the fundamental theorem of calculus, this is the same as C of 20 minus C of 0. So before we calculate anything, let's just interpret what is going on here, right? So the fundamental theorem of calculus tells us that the cost to increase production from 0 to 20, right? That's the difference in cost of producing 20 units and producing 0 units, right? That is given as the integral, the definite integral of the marginal cost function from 0 to 20. So in other words, here we have the costs to produce 20, right? Here we have the fixed cost, and this would be the total, what is called the total variable costs to produce 20 units. But we are asked now to find the total cost, right? So we are asked to find C of 20. But we see now how we can find or compute C of 20. We just need to rearrange these expressions here, right? So let's do this. We can write C of 20 as C of 0, right? And plus 0 to 20 C prime of Q dQ. So what is left now is to compute these values actually. Well, C of 0 is given to us, so that would be 500, right, plus the value of this, right, this definite integral. And this brings us to the question of how do we compute definite integrals. Well, so far in the previous lesson we have mostly either used geometry or we approximated using kind of counting boxes or squares, or we used computers. Right? Now with the fundamental theorem of calculus, all we need to do is to actually find an antiderivative of this function, right, as we saw. Right, so let's do this. There is a whole arsenal of rules again how to find antiderivatives, right? So what you essentially have to do is take the various rules for differentiation and invert them, right? So go from the derivative to the original function now. And in the book you will find this. And so in this lesson we're going to do the power rule, we see the exponential rule, log and sine and cosine, so sine, cosine, and so on. So you can look it up in the book, what these rules are exactly look like, and you can then apply the appropriate rule in each situation. So in the next lesson, there's a few more rules we need to use. So there will be substitution, which you can think of is the inverse to the chain rule, and then there's the integration by parts, which is the inverse to the product rule. But we'll get to that in lesson 11. So for this week, these rules here are all you need, and you'll find them in the appropriate sections of the book, right? Specifically section 6.2. So this here is just a combination of power functions. So for this, we can just easily use the power rule to find an antiderivative. So here I applied the power rule for each of those expressions, right? So q squared, you go from, instead of, right, for the power rule for derivatives, we had to decrease the exponent by 1 and multiply by this, right, by the exponent. Now we have to increase the exponent by 1 and multiply by the thing that, by a factor that offsets the fact that if I take the derivative, I have to multiply by this factor 3. So in this case here, 1/3, right, offsets the multiplication by 3 when taking the derivative to get to q squared. Same thing here. I go from q to the 1 to q to the squared, offset and divide this by 1/2 to offset the multiplication by 2 when taking the derivative in this direction up here, right? And then plus 70q. That's the simplest case of the power rule, right? So this is an antiderivative. So all antiderivatives, I would have to add plus c here, right, to get all possible antiderivatives. But as we saw, to compute the definite integral, it is enough to have just one antiderivative, and for that it's good enough. So forget about plus c here, right? We have one antiderivative. So now we know from the fundamental theorem of calculus that the integral from 0 to 20 c prime of q dq is c of 20 minus c of 0, right? And now, so often this is just also written as c of q, and then you write like 0 to 20 here, in the sense to say that you evaluate this function at the upper end and the lower end, and then take the difference between the two. So all we need to do now is plug in, right, take our function c here, capital C, and plug in 20 and plug in 0. Okay, let's do that. So that would be 1/3 20 to the third minus 8 times 20 to the 20 squared plus 70 times 20. And then minus, so this would be the value for c of 20, then minus c of 0, right? But we see, if I plug in 0, I get 0 for this expression, I get 0 for this expression, and 0 for this expression. So all of them is 0, so this would be just minus 0. So all I need to do now is compute this. So this would be 866 2/3. And interpreting this now with respect to our problem, so this is the cost that would we incur if we increase the production from 0 to 20. So this would be the total variable cost to produce for 20 units. So now we have these numbers, right? We can put everything together. So the total cost for producing 20 units was C of 0, which is the fixed cost, plus the integral from 0 to 20 C prime of Q dq, which we just computed. So those were the total variable costs, right? So total variable costs. Right, and now we just plug in the numbers and we get 500 plus 866 2/3. So let me just write it as 0.67. And so the final answer would be 1366.67. And this would be the total cost in dollars for producing 20 units. So the last problem I want to do is a problem of a very similar kind than the problem we did just before with the marginal cost, only that now it's not really in any context. It's just a pure math problem, right? But the way to solve it is the same, essentially the same way that we did just now. So this is 6.1 number 3. Suppose f prime of t is 0.82 to the t, and f of 2 is equal to 9. Find the value of f of b for b equals 2, 4, 6, 10, 20. I'm not going to do all of them, but I'll show you how to do 2 and 4, and then you can do 6, 10, and 20 yourself, hopefully. So, again, basic tool here, fundamental theorem of calculus. So we know that, right, that f of 2 is 9. So this takes care of b equals 2 for us right away. So we can write this right away. So if f of 2 is equals 9. Okay, check. So what about f of 4? Well, we know that by the fundamental theorem of calculus, right, the definite integral from 2 to 4 of f prime of t dt is the same as f of 4 minus f of 2. But f of 2 is already given to us, right? Because that's right. This is the extra information that is given. It is similar to in the previous problem where the fixed costs were given to us. So C of 0 was given to us. Now it's f of 2. So we have to adapt our approach here a little bit. We cannot use 0 here because we don't know f of 0 yet. But we know f of 2, so we just take the definite integral from 2 to 4, which would be f of 4 minus f of 2. Okay. So now we can rearrange this and write f of 4 is equal to f of 2 plus definite integral from 2 to 4 f prime of t dt. F of 2 we know, so what remains is to find this definite integral. We proceed as before. We find an antiderivative, right, of this function f prime, right, which is given to us here, and then evaluate the definite integral using the formula given to us through the fundamental theorem of calculus. So how do we find an antiderivative of 0.82 to the t? Well, that looks like a complicated function. Well, we have a rule for this. This is, in general, an exponential function. And we just do a little trick of rewriting it as e to the ln 0.82 times t. Right? Remember, any kind of power function can be rewritten as a power function with base e in this form. For this now, we can actually use the exponential rule. So we know that the indefinite integral e times kx dx is equal to 1 over k times e to the kx plus c. Right? So in our case, k is equal to ln 0.82. So what we would have here, we just need one antiderivative, right? So we would just say, okay, here we have 1 over ln 0.82 times e to the ln 0.82 times t. So this is our antiderivative. One antiderivative, but that's all we need to compute the definite integral. And here is then our integral. So definite integral for this function is this antiderivative evaluated at 4 minus this function evaluated at 2. So you can plug this now into a computer or calculator. And this gives us approximately 1.11. So now to get f of 4, we just remembered this was f of 2, right? Plus this integral here, right? So this integral, so plus 1.11. F of 2 was 9. So this would be 10.11. Let's do one more value. Right? So we want to do f of 6. F of 6 would be now by the same formula. So now let's start again with the fundamental theorem of calculus. Would be 2 to 6 definite integral of our original function f prime of t dt, right, which is just this function up here, right? That's equal to f of 6 minus f of 2, because we know f of 2 already, right? So that allows us to rewrite the whole thing then as f of 6 is equal to f of 2 plus this integral from 2 to 6, da, da, da. You could, since we now know the value of f of 4, you could also work with 4 here in place of 2, right? But that's really up to you. It really doesn't matter. You just have to, if you go with 4 here, you of course would have to subtract f of 4 here. The nice thing now is that we essentially have done all the work already, right? Because if you look at this, we now need to evaluate this definite integral from 2 to 6. But by the fundamental theorem of calculus again, this is just evaluating this function at 6 and at 2, right? At 6 and at 2, and subtracting the 2 from each other, right? So we can reuse the same expression, because once we have an antiderivative, it is an antiderivative for every point. So not only for 4, it also works for 6, right? So we can just do this. Plug in 6 here, subtract 2, right? And you get this definite integral. Subtract the value at 2, not 2, of course. So I did this quickly on my calculator, and I got, now this is 9 plus 1.856. So the value here would be 10.856. You see that the basic pattern is the same, right? So you just plug in the different values here. But once you have the antiderivative, it's actually quite easy to compute other values now. And I'm not going to do this, but I hope you know now how to proceed, for instance, to get f of 10 or f of 20. Right? It's just replace the 6 here by 10 or by 20, right? And reuse this expression. Okay, so I hope this gave you a little bit more insight on how to use the fundamental theorem of calculus. A lot then will now just depend on finding antiderivatives. So we've kind of, I've tried to stress in the problems that I did in this lecture how the fundamental theorem of calculus is used conceptually here. A lot of the remaining things to be done, especially with respect to the technical aspects, is just to now find rules how to compute or find antiderivatives. And this will be a big chunk of the next and final lesson, namely the substitution rule and the integration by parts rule. Okay.